momentum, that's our first example on that. Let's do this again, but let's come from a different type of problem. It's the same type of experience that we're looking at, but now we're going to look at this a little bit different. So our second example is going to be this example 6.2. Now remember, this is the same process as before. So let's go look at this thing here. So it says here in the Little League baseball game, a 145-gram ball enters the strike zone with the speed of 15 meters a second. The batter hits the ball and it leaves his bat with the speed of 20 meters a second in exactly the opposite direction. Here's what I want you to do. Draw the impulse momentum bar diagram for this situation. Draw me a picture and then draw what the impulse looks like. Okay, let me give you a minute to actually do that, and then I'll start on it. Okay, so answering Ian's question here, that is the definition of momentum. So if I come back here up to the very top, we defined P as momentum, which is mass times velocity. So when I look at the impulse momentum, it is telling me that that is that. In other words, when I look at the definition of momentum, and it reads like this, it is, assuming that the mass is the same, it's going to be mv2, mv1, and that will be the change in momentum if the system does not change its mass. And in this course, we don't have that because it gets complicated too fast when the mass changes. We have to use calculus then. Okay, let's look at this guy. So what I want to do here is that I want to draw, or maybe I should say I want to interpret. Okay, so I want to interpret the problem. Okay, so what do I see here? Well, the first thing that I'm going to do is that I'm going to imagine that the baseball is moving to the left. So I have a baseball that is thrown. And so I see that this baseball is now moving in this direction, and it has some initial momentum. Now, what I have a tendency to do is that I typically pick the direction of the ball when I'm going to have a change in direction. I'm going to pick that this is my negative direction, and then this is my positive direction here. Now, what about the bat? Is the bat moving? We don't care what the bat is doing. All we know is that there is a bat here. And we don't envision the world as the bat is actually moving here. What we see here is that the bat is stationary. And what the bat does, it implies an impulse in the opposite direction. Afterwards, what happens here? Afterwards, what happens here is that now what I focus on is that I'm only focusing on the ball, because we never bring into the question what the bat is doing. So this is the before. So then afterwards, the ball is now moving in the opposite direction, And according to the speeds here, the momentum of P2 is now higher, but it's now going in the positive direction. So what you're seeing here is that I'm setting up this before and after, where I'm only focusing on the ball itself. So what does this tell me about the bar diagram? What the bar diagram says that the initial momentum of the ball is negative. And the way I show that it's negative is that I draw it below my axis like that. So that is negative. So what does the bat do? The bat now comes in and it changes the momentum of the ball. Now note that the ball is now moving to the right, so it has to be positive. So then what we're saying here is that, let's say that the ball now has this much momentum, P2. So the key thing here is that you can see here that the momentum here starts negative direction, and now it ends positive direction. So now what happens here? And you know what? I'm going to run out of space. So let me move this down a little bit. Okay, let me move this down to right here. And so here we go. So what's the first thing that the bat has to do? Let's go get that picture again. Okay, let's get that picture again. The first thing the bat has to do here is that what does it has to do? It has to stop the ball. So the impulse, as the ball is coming this way, the impulse is being applied in that direction here. This is the impulse of the bat. So the first thing that the bat has to do here is it has to stop the ball first. And that's why this P1 and this impulse that I drew in red are equal and opposite. Because you have to stop the ball. Now, what do I have to do? I have to speed up the ball. How much did I speed up the ball? So what you're seeing here is that if this thing is worth 3 squares, then that means this has to be 3 squares as well. And this is what speeds up the ball right here. So this piece right here, this speeds up the ball. This stops the ball. That's what that picture should be showing you here. And again, you're seeing here that the impulse continues of the bat to move in that direction. So according to the impulse momentum theorem, that's what it is right there. So that's our mathematical equation where this is the impulse of the bat. So now what I want to do here is that if I now go back and look at the question here, is they're asking, what is the magnitude of the impulse delivered by the bat to the ball? Well, the way we answer this is that we still use the impulse momentum theorem. So here we go. So the impulse momentum theorem says this. According to our picture, look at our picture here. Look at the momentum of P1. Our picture then says that the momentum P1 is negative, and then our impulse, J of the bat, is positive, and then this is going to equal to P2. It tells us what the signs are. So now, what do I know here? Here's what I know. What I know about this thing, they tell us what the mass of the ball is, which is 145 grams or 1.45 kilograms. Right? That's the speed of the ball, the mass of the ball. Now it has a speed of 15 and it has a speed of 20. Note, we've already included the signs. So then that tells me here is that the speed of 1 is 15 meters a second. The speed of 2 is 20 meters a second. So now I can solve for the impulse of the bat. So now the bat's impulse is then going to be what? I'm going to have J bat, and that's going to equal, look what happens to P1. It now becomes positive. So this becomes P2 plus P1, and this will be the mass times the velocity in each of these situations. Note that the mass is the same. So then this will be mass times V2 plus V1. So now I'm just going to go in and I'm going to put in my numbers here. So this should be 0.145 kilograms times the quantity 20 meters per second plus 15 meters per second. And if I compute that, I get a value that reads 5.08 Newton seconds for the impulse of the bat. I now know what the impulse of the bat is. So now that I know what the impulse, let's go to part B. Part B says that if the bat is in contact for 1.5 milliseconds, what is the magnitude of the average force exerted by the bat and the ball? So let's look at B now. So B now says, what is F average if the contact time, delta T, is 1.5 milliseconds? Well, by definition of impulse, what do I write here? It says here that the impulse is the area, and by the mean value theorem of integrals, I can write this as the time to average force times delta T. Note, we already calculated J, so now I can solve for the average force of the bat. So then, solving for F average, you can see here is that F average is then going to be the impulse divided by the time. So in this case, this is going to be 5.08 Newton second, and then this is going to be 0.0015 seconds. So this gives me a value of 3,400 newtons for the average force. And there is my average force right there. So what is this? Well, that's like 3.5 times my weight. So that is a lot of force acting on a baseball.